So now let's talk about Taylor's theorem with remainder. So let f be a function that can be differentiated n plus 1 times on the interval I containing the real number a. Let Pn be the nth Taylor polynomial of f at a. Okay, so now let's see what that looks like. This is what that polynomial. So here's the Taylor polynomial. So first f of a, f prime of a, x minus a, and then f double prime, and so on and so forth, all the way to f nth derivative of a over n factorial. So now that's what my Pn is. So essentially what I'm doing is I'm taking my f, which is the function we're trying to approximate, and we're minusing the Pn off. And when I minus that Pn off, that's going to be the Rn. So if I think about this, if I just kept going all the way down, that would be my Rn. Okay, because I have my f and I'm going to minus the P, and then everything else after that is what I'm going to have left. So that's what that remainder is. What's cool about it is how I can actually find this remainder. What it says after this, it says let that be the remainder. So this is my Rn here. And then it says this, then for each x in the interval I, there exists a real number c between a and x. So I'm thinking about this on a number line. There's my x. And I'm thinking about c is between there somewhere, such that Rn actually equals the remainder. Oh, so such Rn equals this thing here, which is the n plus 1 term of the Taylor polynomial. So think about this. If I just went one more term, that would be that term. And that's what it's saying, that Rnx is going to equal that next term. And my c is going to be between the a and the x. Okay, so that's what it's saying. So that's my equality I get, which is nice. So now, if there exists a real number m such that this nth derivative of f can be bounded by that number for all x and I, then I can actually find an error that Rn can be smaller than. So that remainder can be bounded by some number. And that's what we're going to find. And that's what's cool about this theorem, because if I can bound this n plus 1 derivative, the cool thing about it is then I can say, okay, well, if I want this function f, I want to be duplicated, and I go over 3 terms, I could say 3 terms, or 4 terms really, but to the third derivative, then I can say, hey, I'll be in this certain amount of error. And that's the power of this inequality down here. So that's what we're going to do now. So let's play around with this, and then you can see a little bit more of what this power that we have here is. So here we go. All right, find the smallest value of n such that the remainder estimate, Rn less than or equal to m over n plus 1 factorial x minus a to the n plus 1. Now take a look at this. This is just what we see down here. And that's what they're getting at here. Okay, anyways, where m is the maximum value of f. Now, I like to think of this way. So when I see that m is a maximum value of this f n plus 1z, I think of this inequality right here. In my head, that's what I see when I see that. Okay, I'm looking for that m now. Okay, and then it says on the interval between a and the indicated point yields Rn to be less than 1 over 1,000. So that's going to be our parameter that we're shooting for here. And then it says on the indicated interval. So now on this interval, for this function f of x equals e to the negative x, we want to be on this interval from negative 3 to 3, and we're going to take our Taylor polynomial out far enough to where this remainder that I have is going to be less than 1 over 1,000. So the first thing we're going to need are n plus 1 derivatives. So let's take this and work it out. So f prime of x is equal to negative 1 e to the negative x. F double prime of x equals negative 1 squared e to the negative x. F triple prime of x equals negative 1 cubed e to the negative x. Now hopefully one thing you notice here, I'm not multiplying them all out because I don't really care about the numbers themselves. I care about the pattern. So now if I kept doing this, I'm going to get f of n, let me do n plus 1. And that's going to equal negative 1 to the n plus 1 e to the negative x. Now that's what my n plus 1 derivative of f is going to be. So here I just kind of want to show you what that actually looks like. Now here I graphed it, but I was assuming that this n plus 1, this negative 1 to the 1 plus 1 was going to result in a positive 1. So then if I graph this, notice this is my function here. Okay, and I even put the numbers negative 1 and negative 3 in there, and that's what we see with these red lines. And if we see, it's actually a decreasing function, so its largest value is going to be here. And I also put that in for you guys here with this green one. So that's really, you have to type it out. So this is really e to the 3. So what that's saying is its largest value, if my negative 1 n plus 1 part was positive, it would be e to the 3. Okay, now I want to show you the other side of that. Assume it was negative. Now if it turned out to be negative, I put both graphs in there so you could see them. Then it would end up down here. And guess what that is? That's also, that's actually negative e to the 3. Now notice what we're doing with these though. This is the absolute value of n plus 1 z here. So that means no matter which one it is, I'm going to take the absolute value of it. And we'll see that they both result in the same value. So that tells me on that closed bound from negative 3 to 3 that we would end up with e to the 3 as our maximum. It doesn't matter if it's positive or negative because when I take the absolute value of it, it's still going to result in that e to the positive 3. So now we can say that this absolute value of this is less than or equal to e3. And I can say less than or equal to because keep in mind here, I still have all these values here. Now what is the c there then? The c would actually be here at negative 3. So that's kind of how I would think of it. So now Rn of x equals this thing here. So that means the magnitude of Rnx is going to equal the magnitude, or the absolute value I should say, fn plus 1 c over n plus 1 factorial times x minus a n plus 1. So the absolute values are going to be the same. They're going to be equal. Which then we know that this fn plus 1z is going to be less than or equal to m. So then what I get is this. And this is where we're going to start. And I know m now. What do I know m is? It's going to be e to the 3. So then this is less than or equal to e to the 3 n plus 1 factorial. X minus a to the n plus 1. I did forget one piece of information here before I can move on to the next step. I forgot to write that in. I apologize. It's a equals 0. Okay, so anyway, so that means we're centered at 0. And honestly, I could have put that in all along, but that's okay. It doesn't matter. This is a nice general way that I can look at this. So I know my a now is 0. And honestly, that only changes this piece right here anyways. I could have just called it absolute value of x all along. But anyways, doesn't matter here or there. That's just where it comes in at. So now I'm just going to plug everything in. So it's going to be e to the 3 on top, n plus 1 factorial on the bottom. And this is going to be x. My x is negative 3, remember that? That's what gave me my largest value. And then minus 0 to the n plus 1. Okay, now I'm going to just simplify this and put everything together here. So then this is going to be e to the 3 over n plus 1 factorial. And then this is just going to be 3 to the n plus 1. Now remember what this is. This simply means that, hey, this is less than or equal to my Rn of x. So that's my bound for my Rn of x. So now what we're going to do with this bound is now we can use this Rn, this absolute value of Rn of x being less than or equal to 1 over 1,000. So now I'm just going to write out this inequality. So this is that inequality we're looking at here. Now we want this to be less than or equal to 1 over 1,000. So now the way we handle this, once we found out that bound for our Rnx, is we really just want to try numbers. And I think that's the best way to go with this. So for instance, let's try n equals 1. And then with n equals 1, is that going to be less than or equal to 1,000? I want to get as close as I can to 1 over 1,000. So then once I punch this all in, my calculator here, I get approximately 90.384 blah, blah, blah. So again, so then I try 2. So n equals 2. And then I run through the same process. So that is really this here, that actually equals here. And then this approximates to 90.384. Now it looks like it's about the same. So that tells me that I might have to go a lot bigger. So I might try maybe 5 or 10 next. So I'll try 10. Oops. And see if we're getting any closer. Now this one here is getting closer. That's 0.0891 blah blah blah. And again, I want to get to 1 over 1,000. So what is 1 over 1,000 as a decimal? That would be 0.001. Now I'm not quite there yet. So now I'll go 15. See if that gets me closer. Now that one turned out to be 0.000041. So that went too far. So I'll go one less, I guess, here. I'll go to 14. Now that also still seems too far. So now I'll go 13. And that gave us 0.0051. So that actually went too far. So actually, this one isn't smaller than it. But this one is the smallest one I can get. I mean, that gets the closest to it as well. All these other ones above it are smaller. But I want the largest possible n that is smaller than the 1 over 1,000. So it turns out to be this one here. So we're going to be at n equals 14. Now let's take a look at what that means. So now, if I take these values here, and this is kind of what I did, I just kind of started them. I want you to see this. So now f prime of x is negative e to the negative x. And then I'm thinking of f prime of 0, and that equals negative 1. And then when I do each of these derivatives, what comes to find out is I see this nice pattern. So the second derivative turns out to be positive 1. The third derivative turns out to be negative 1. The fourth derivative turns out to be positive 1. So I have this alternating pattern where I have even derivative, it's positive 1. Where I have odd derivative, it's negative 1. So all I'm going to do is I'm going to fill in the Taylor polynomial, and I'll show you what that is in a second so you can see how that works. But remember, any odd derivative is going to give me a negative 1. So then for this thing, when we plug in those f primes of a's and f double primes of a's and all those, that's what we're going to get. And also our a is 0 here too, so that's what makes this a really nice problem to actually work out. So this tells me I'm going to go out to 14. So let's see. So then for the first one, if I was going to do a P14, my first one then, where my a is 0, that's my original function. So that would be e to the negative x. So if I plug in a 0 there, that's going to be 1. And then my next one, the f prime of a, remember that's a odd power, so then it's a negative x. Okay, and then my next one, if I kept going with this, my double prime would be a positive 1, and that would be over 2 factorial, so over 2x. Now I'm just going to continue this pattern out to 14. And don't forget my 2 here. Okay, and then I'm going to keep going. So here's that polynomial. Doesn't that look terrible? Now look at this when I graph them both. Now I graphed e to the negative x and this polynomial here, which looks awful. And I just want to kind of show you that we had to go out 14 for that. So now take a look at this. So here it is. So now the green one here is my exponential, so that's this one here. Okay. And then the other one is the red one. You can't see half of it because it looks like it's sitting right on top of the other one. It's really not, but it's very close in most places. And that's what we'll see. So again, as you can see, now on the interval, now between -3 and 3, this thing is going to be, the error is going to be less than that 0.001. And that's what's kind of cool about it. I want to show you a table now. Now take a look at this table here. Remember, it was from -3 to 3. And if you look at here, this doesn't go that far. I got it from 1 to 3 actually, so here. But I wanted you to see after 3. When I look after 3, actually let me look before 3 first. If I look at all of these numbers here, this first column here is the polynomial function. This is my e to the x here, that second column. So anyways, when I match these numbers up, notice they're exactly the same for quite a ways out for a lot of them. But if you look at number 3, notice this. It changes on the fourth one, but it's still definitely under the 0.00 is it 30? Yeah, 3001 error that we're supposed to be better than, and we are right here. But and that only goes up to 3 now because this is actually 0001. Right? Is that right? Yeah. 1, 2, 3, 4. Yep, 0001. Yep, there it is. Okay, so anyways, so now looking at that, but when I go past that 3, oops. So when I go past the 3, notice this. So at 4, it's still pretty good because it's still past the 0.001. But now look at number 5 here when I go to 5. And that's going to be 1, 2, 3, 4, 5. Now look at the error there. It's it's a lot larger than that 0.001, as you can see, because this is the first number. I'd have to be at least accurate up to those digits, and I'm not. So it just goes to show you that it works on the interval we actually set up, which is pretty cool. Ours is actually a lot more than that, but I want you to see something. So our R14 of x, and I'm just going right back to the top here, right up here, is going to equal 3 to the 15 e cubed over 15 factorial. And that number turns out to be this number right here. So that's the number that we're actually going to be less than for all of our between. It's going to be the most amount of error that we could have using that P14. All right, there it is. That's actually all we needed. I put a lot of that information in, and you didn't really need it, but that's about the gist of it. So just keep in mind, I didn't have to put the polynomial in. I didn't have to show you all those graphs. But I did want you to see kind of what this means when I find this error, and what this n equals 14 number I find actually means for us. That if I do a polynomial that is P14, that Taylor polynomial, that it's going to be within that 0.001 error, and I can't get any closer without going over. So that's it.